All right. Good morning, everyone. And welcome to the general session 17 of TÜBA World Conference on Energy Science and Technology. So this, I'm Hasan Özcan. I'll be chairing this 90 minutes session. And there will be 6 presentations. And we have 90 minutes for this. So that means for every presentation, we'll have a total of 15 minutes. That's why I strongly recommend you to finish your presentations each in 12 minutes and then a couple minutes for the QA sessions. The first presentation of the session is titled as Development and Analysis of a Novel Greenhouse Roof for Reduced Cooling Load in Hot Climates by Yusuf Bicher, Mohammed Usman Sajid, and Mohammed El Breiki from Hamad bin Khalifa University from Qatar. I don't know if the panelist attendees can unmute themselves. I'll anyway ask Mr. Bicher to unmute himself and share his screen.
Dr. Hassan, can you hear me?
Yes, yes, we can hear you.
Okay. Okay, then let me make the full screen and I will start. The screen share is okay?
Yes, everything is okay.
Okay.
Thank
you very much. Today is the last day of the conference and the first presentation, so I don't expect many people, but still, you are welcome to listen and then report later on. And thank you very much for your attendance. Let me open the video as well. The topic of today's presentation is the development and analysis of a novel greenhouse roof for reduced cooling in hot climates. So what we are trying to do is how to raise greenhouse crops in hot climates in a sustainable manner. This project was done by my research group, our students, Mohammed Usman Sajid and Mohammed El Breiki. The outline of the presentation, first, the problem statement. What is the problem existing at the moment and our objectives? Later on, some introduction about the greenhouses and our analysis and results and discussion. Later on, we will conclude the presentation. So the main problem is the food security, how to grow crops in hot, arid climates. Most of the time, as you know, we have open land areas for crop production. But when it comes to hot climates like 50 Celsius outside, we have to sustain the temperature at the desired levels in a controlled environment. So this brings us to the greenhouses. As you know, the greenhouses, we have the plants. The plants do not utilize the full spectrum of the solar light because of their nature. So they are only active in so-called PAR level, photosynthetically active region, which is ranging from 400 to 700 nanometer. During the photosynthesis, and the efficiency of the photosynthesis is not also 100%, there are some losses to the greenhouse heat dissipated. Especially after 700 nanometer, the extra spectrum that is available inside the greenhouse causes overheating. So this also increases the cooling load in these hot climates. So what we design here, let us try to develop a new greenhouse roof that can track the sun during the daytime for power production with solar PVs. And that can also optimally manage the spectrum, which is not normally used by the plants. So unwanted spectrum is utilized by power production. So this will also cause a reduction in the cooling load, and we are able to produce at least 50% of the cooling power required through the PVs on the roof. Of course, there are many attempts in the literature how to manage this cooling in the greenhouses. One of them is evaporative cooling. Evaporative cooling is mainly used using these evaporative pads. You circulate the air through these pads. However, the humid nature of the air causes some damage on the plants, and especially for extra humid coastal regions, this cannot sustain very well. There are also some attempts like fresnelnesses and organic photovoltaic cells, and they put them on the roofs of the greenhouses, where either they filter the solar light or they block it partially. There's also pink type filters that block the solar spectrum, but that causes over blocking, which causes extra cooling load again. In a conventional greenhouse, we don't have anything on the roof, just a greenhouse roof with a transparent plastic or glass. And this is causing the extra solar spectrum to be in the greenhouse. One good approach is to have partial shading with semi-transparent PVs on the roof, which has enough solar light in the greenhouse, but still they do not absorb the spectrum over 1100 nanometer, which is still causing some overheating. So when it comes to our design based on the literature, let us try to develop a new design. We had a solar tracking roof here mounted on the greenhouse itself with the transparent dielectric mirrors and the semi-transparent crystalline silicon photovoltaic cells. In addition to that, we have a vertical aligned indium gallium arsenide photovoltaic cells. So here the electric mirrors reflects the infrared spectrum to the vertical aligned indium gallium arsenide photovoltaic cells for power production. In this way, we utilize the minimum area in the roof by using it vertically. And the electric mirror also transmits only the visible spectrum to the plants, which is 300 to 700 nanometer, used for the photosynthesis. So in this way, we do not damage the plant photosynthesis process, and we produce extra power from the roof by using the spectrum in an optimal manner with silicon photovoltaic cells and indium gallium arsenide photovoltaic cells. The reason why we chose this type of PV cell is because it is sensible after 700 nanometer. It can produce after 700 nanometer power. So after designing the system, we have to calculate the cooling load by considering the radiation, the cover, convectional heat transfer, the crop transpiration, reflected spectrum also, or ventilation in case we have window openings. Once we calculate this each heating load, including the crop transpiration, which will also cause some cooling load in the greenhouse. And the crop evapotranspiration, of course, depends on multiple factors, including heat of vaporization of water, psychrometric factor, or leaf area index, which will change based on the plant. But here we have to select a type of a plant from the literature. Then we have also come up with these calculations. Once we have the greenhouse model, we need to simulate the solar light hitting on the greenhouse. So for that reason, we have used smart software developed by NREL, which gives us the direct diffuse and tilted irradiance for each location of the greenhouse and for the walls of the greenhouse. Because through the walls, we have still a lot of solar radiation input, which is not filtered. Our approach is only for the roof, but even for the roof, we have significant reduction in the cooling. In addition, we have considered a ventilation window, which is a normal case for many greenhouses, but it is a natural ventilation, which will reduce the cooling slightly. But in hot climates, you will see in the coming slides, it is not effective anymore. First, we validate the model by comparing with another study in the literature. They have also conducted a greenhouse simulation under these desert conditions. So this is the inside temperature of greenhouse if it is not externally cooled down and if it is only ventilation through the window. And it is for Qatar here, the outside temperature in the summer, the range is from 40 to 50 Celsius. So that's why the temperature in the greenhouse can reach up to 55, 56 Celsius. For the other model, it is also similar trend. The deviations might cause because of the different climate, different location slightly, but the trend is the same. When we come to the results and discussion, we compared our cooling load, which is the proposed design, with a conventional design having only ventilation. The proposed the normal greenhouse here, the conventional one, is the highest with a cooling load of 32 kilowatt at peak time. If we set the temperature of the greenhouse to 23, the set temperature of the greenhouse may also change based on the plant type. Mainly, it is ranging from 20 to 28 Celsius. Here we have selected two set temperatures, 23 and 28. When it is 28, for some plants, 29 kilowatt peak load is required for cooling of the greenhouse. But in our case, when we have the solar tracking roof and blocking of the sunlight, unnecessary sunlight, at 23 set temperature, we were able to reduce the cooling load to 23 kilowatt almost at the peak time. In 28 Celsius set temperature, it is even 20 kilowatt. Here, one important thing to note is that in the mornings and in the evenings, let's say after noon times, the cooling trends are similar. Why? Because we don't have the sunlight at the noon. The solar radiation is hitting through the walls. The walls are not changed. That's why we have cooling loads similar. But at the peak time, we have significant reduction. And one other advantage is that at this peak time, we produce the most power from the photovoltaic panels in the roof, where we have the highest solar irradiation. And here, this graph shows the produced power and the required power by the cooling load. So we have two types of production, electricity production from the roof. One of them is silicon, the other one is indium gallium arsenide cells. As you see here, for some of them, we produce more power in the mornings because of the solar tracking. It is around 1.5 kilowatt for the silicon cells. And for the gallium arsenide cells, the dark red line, we produce more power afternoon, where we have sunlight exposure the highest, up to 1.2 kilowatt. The required power, on the other hand, is almost double of this. Even for cooling down this greenhouse, we still need up to here 8 kilowatt in a conventional, but almost 4 kilowatt in our proposed design. So we are able to produce almost half of the required power on average from the roof. So in conclusion, we have also different aspects of the analysis where we have a monthly analysis for 1 year and comparing the winter and summer cases as well. In the winter case, we are able to fully satisfy the cooling load from the power generated on the roof. But in the summer where we have the peak load, only 50%. So it means we need to maybe install additional solar PVs on the side of the farm, but it will require less area. So overall, a novel solar tracking roof is designed for greenhouses for securing the food production in hot arid climates in greenhouses. The roof tracks the sunlight 30 degrees to 60 degrees, especially between 11 a.m. to 2 p.m. And it will produce more power during this time, up to 30% more compared to fixed roof. And during the summer period, for set temperature of 23, the maximum cooling load reduction is achieved as 29%. So on the 28 Celsius set temperature, we reduced cooling load by 32%. As we have discussed, we can sustain the self-sufficiency up to 50% in the summertime if the set temperature is 28 Celsius. So the analysis still continue. We will try to make the experimental work for this study as well by using the reflecting mirrors and the silicon cells and gallium arsenide cells. Hopefully the experimental results will also confirm the simulation. These are the references we have used, and thank you very much for listening. I hope it was beneficial and satisfactory for you.
Okay, thank you for your timely presentation. I see there are a couple questions.
Okay.
How did you design overall panel dimensions and greenhouse dimensions?
Very good question, in fact. So we tried to develop a greenhouse that is suitable for even gardens of the houses. The dimensions is 4 meters to 10 meters, 40 meters square area. So we said it is like a ship container where you can place it anywhere you want. So that's why the roof design, the panel dimensions is based on this 40 meters square land area. We have tried to maximize the power production from the roof. First, place the silicon cells and then the gallium arsenide cells vertically. So basically based on a small design where you can place it anywhere, 40 meters square greenhouse is used.
All right, thank you very much. So the time is up actually for this presentation. We'll ask no more questions, and thank you very much for your presentation, Yusuf.
Thank you very much. Thank you, successful conference in the coming hours.
Thank you. The next presentation is titled as Development and Validation of a Dynamic Thermal Model for a Water Wall Integrated Indoor by Nilay Altunacar, İbrahim Şener, Yonca Yaman, Berkay Budakoğlu, Erdem Topkara, Ayça Esmer, Mehmet Akif Ezan, Ayça Topuç, Gülden Köktürk, and İrem Deniz from 9 Eylül and Manisa Celal Bayar Universities. Is Nilay ready for the presentation?
Yes, can you see my screen?
Yes, screen is here, video is here. Okay, Nilay, please try finishing the presentation in 12 to 30 minutes, please, and then we have time for the Q&A sessions.
Hi, everyone. First of all, I want to thank everyone for being here today. Let me introduce myself. I am Nilay. I am a mechanical engineer and master student at 9 Eylül University. As you can see on the screen, my topic today is development and validation of a dynamic thermal model for a integrated indoor. First of all, I will talk about and what is its purpose. Then I will talk about the classification of the indoor thermal modeling. Secondly, I will introduce the system we are working on and the system we have chosen for validation. Then I will briefly explain the modeling steps through the flowchart. After that, I will talk about the preliminary analysis, validation, and parametric analysis and their results. Finally, I will talk about what we plan to do in the future studies. We can examine the purpose of indoor thermal modeling under two subtitles. The first is to determine the thermal comfort of human body. The thermal comfort of human body depends on personal factors such as metabolic rate and clothing insulation, and environmental factors such as humidity, airspeed, air temperature, and radiant temperature. So in order to determine the thermal comfort, these environmental factors must be obtained experimentally or numerically. When experimental work is not possible, indoor thermal modeling is used. Another purpose of indoor thermal modeling is to predict energy consumption. Thanks to modeling, energy consumption can be predicted while a building is in design and can be ready. Modeling types can be divided into three main groups according to the way in which the local temperature effect of indoor air is taken into account. The first is lumped approach. The second is 2- and 3-dimensional thermal modeling, and these are nodal and zonal models. The third is computational fluid dynamics. The lumped approach accepts a single temperature representative of the indoor air, completely ignoring local variations. The outdoor temperature is reduced to a single node with a similar principle. It reduces the solution time for long-term numerical analysis. Cases where a lumped model is insufficient in case of displacement ventilation, underflow air distribution, cold beam regions, natural ventilation, mixed mode ventilation, long or large spaces. In other words, this model is insufficient in cases where fluid circulation is high. Nodal or zonal models are used when lumped models are insufficient. Here we see two different examples of use of a nodal model in the case of convective heating. In the model on the left, developed by Howard, the room is examined with two nodes, lower and upper. In Ardembuty developed this model and defines nodes close to the ceiling and floor, a node in the room, a node in the heater, and a node close to the heater. Zonal models are based on the principle of dividing the volume into subregions. They can be called an intermediate approach between CFD and nodal models. Here, local velocity values are obtained through simplified relations. Different subcategories of zonal models are due to result variables such as temperature, pressure, and momentum. In the CFD methods, Navier-Stokes equations are solved iteratively for the entire solution region, and indoor temperature, velocity, and pressure distribution can be determined. Very detailed solution can be obtained even for complex geometries. Situations where a CFD is insufficient, actually it increases the solution times in long-term numerical analysis and requires high-performance computer depending on analyzed geometry. Let me introduce the system we are working on within the scope of a TÜBA project. One facade of indoor indicated by 2 is surrounded by photobioreactor indicated by 1. And algae growth takes place inside the photobioreactor through the solar simulator indicated by 3. In the project, we aim to obtain the thermal and luminous effects such as facade element on indoor numerically and experimentally. We decided to validate the indoor thermal model that we will create with a reference model. As I mentioned, there are different types of indoor thermal modeling in the literature, but studies on a mathematical modeling of the water wall or PBR integration are limited. Of the water wall integrated indoor and the reference the study of Lee. In this study, the long-term thermal behavior of 2 identical indoor was experimentally tested in Sydney climate, and the mathematical model results were compared with the experimental results. In one of the indoors, a water wall was used as a facade element, and in the other, a concrete wall was used. Here we see the schematic representation of the mathematical model in the reference study. The calculation zones from outside to inside are as follows: perspex plate, water column, perspex plate, indoor air and insulation plate. The red arrows indicate the radiative heat transfer on the surfaces. The blue arrow represents the convective heat transfer on the surfaces. Heat conduction in solid materials is indicated by pink lines. The progress of solar radiation through the layers is illustrated with yellow line. Radiation undergoes some refraction within the water depending on the layer surrounding the water. Let me talk about modeling. We used lumped approach in fluid regions while meshing the solid regions. We used the explicit method for temporal discretization of the energy equation and central differences for spatial discretization. I can summarize the modeling step like this. I have an initial temperature for each node, and I have time-dependent climate data such as outdoor temperature, wind speed, and solar radiation. With these inputs, the thermophysical properties of the fluids and radiative and convective heat transfer coefficients are calculated at each time step with functions depending on temperature. The heat transfer equation are so for each node, and the temperature of each node in the next time step is found. Since the explicit method is used, this new temperature is used in the next time step and continues in this way. When using the explicit method, the definition of mesh number and time step size is important for accuracy and reliability of the results. So firstly, we change the time step size to test the time step independence of the model. It was observed that there was no significant change in air and water temperatures depending on time, and we set the time step as 1 second to present the validation results. To test the mesh independence of the model, analyses were performed for 2 mesh structures proposed in the reference study. When the mesh number was increased, it was observed that there was no significant change in air and water temperatures, and it was considered appropriate to use 11-node mesh structure in solid regions. We conduct the studies corresponding outcome for Sydney climate data, and this is how we got the air temperature when we run the model with same inputs. The current predictions show a similar trend as in the numerical and experimental findings of the reference study. We checked the mean difference of our results from numerical and experimental results, and we found that the mean numerical difference was approximately 11%, and the mean experimental difference was 9%. Similarly, the water temperature predictions show a similar trend as the numerical and experimental findings of the reference study. We found the mean numerical difference was approximately 11%, and mean experimental difference was at 12%. Then parametric analyses were carried out with a different facade structure. It can be said that the change of the facade material has a great effect on the daily peak air temperature. For example, if we look at this day, the peak temperature of double glazing is approximately 42 degrees Celsius, while it is 36 degrees Celsius on the water wall and 22 degrees Celsius on the opaque wall. The mean indoor air temperatures obtained with double glazing, water wall and opaque wall are approximately 19.7 degrees Celsius, 19 degrees Celsius and 15.5 degrees Celsius respectively. Further parametric analyses were carried out by changing the thickness of water column. Increasing the thickness of water column results in smaller water temperature fluctuation. In addition, it is seen that the daily peak air temperatures decreases with the increase in the thickness of water column. I want to briefly talk about what we plan to do in the feature studies. In our study, we assume that the entire facade consists of a water wall. In feature studies, we aim to model a system in which part of the facade consists of a water wall and rest of the facade consists of opaque wall material, and percentage of the water wall area changes. As I mentioned, we want to model a facade with PBR containing algae in our project. So we want to include algal effects in our model. I want to share with you the results of a 14-day experiment that we have done for this in our project. In the experiment, started with 10% inoculation, light transmittance was measured by spectrophotometer for 14 days. Due to algal growth, the optical density increases and consequently the percent light transmittance decreases. It can be said that the algae create a shading effect in a system containing a water wall. And in feature studies, this effect will be included in the model. In feature studies, we aim to make analysis for different climatic conditions. I would like to show you the preliminary results of the annual analysis for Izmir, Turkey. As can be seen, indoor air temperatures change when the facade on which the PBR is placed is changed. In feature studies, we want to examine the effect of orientation under different climatic conditions. Thank you for your attention. I hope you found this presentation useful.
Thanks, Nilay, for your presentation. Any questions? Let me see. Okay, there are no questions, and sure these are preliminary results. So there will be further results we're expecting. Then we'll see what will happen. Okay. The next presentation is analysis of optimum flow rate of a photovoltaic thermal system integrated with phase change materials by Canan Kandilli and Burak Mertoğlu. Is Burak or Canan, any of them here?
I will present. Can you hear me?
Yes, we can hear you. We can see the screen you're sharing.
Okay, thank you.
Please limit your presentation to 12 to 13 minutes
Okay.
in case there are QAs. Yeah.
Okay.
The screen is yours.
Dear Chair, dear participants, good morning. First, I would like to introduce myself. I'm Associate Professor Dr. Canan Kandilli in Mechanical Engineering Department, Uşak University. I'm also Head of Energy Division. My main topics, photovoltaic thermal systems and concentrated solar power. We have a highly developed energy laboratory for solar energy application, and we would be very happy to welcome you in our lab if you want to visit. Today, I will present our study that my master's student and I complete The title of the study is Analysis of Optimum Flow Rate of a Photovoltaic Thermal System, PVT, Integrated with Fast Change Materials, PCM. In my presentation, first I will mention solar energy, then I will introduce PVT systems integrated with PCM, aim of the study, system description, result and discussion, and conclusion will be explained respectively. As we all know, solar energy has some advantages. Solar energy is plentiful, clean and renewable, available for local solutions, independent, free. Solar energy gives many solutions for many problems and has low operating cost. On the other hand, solar energy has some disadvantages. Solar energy needs large areas, non-continuous, unsteady. There is a storage problem, high investment cost, and shading problems, especially for PV systems. What is PVT, photovoltaic thermal systems? A PVT system combines PV and solar thermal collectors. We can produce both thermal and electrical energy in a single panel. Each PV material has a specific spectral response. PV panel can convert specific wavelengths into the electricity. Solar radiation that is out of spectral response is transformed to excessive heat loss. This is very important for PV systems. And this excessive heat load causes higher temperature, increasing internal resistance, and to decrease electrical efficiency, both instant and long-term efficiency, electrical efficiency. With PVT systems, we can convert this heat load into the useful thermal energy. So we both prevent decrease of electrical energy. PVT systems can be used for industrial aims and have a great potential for nearly zero energy buildings, that is for NZ. So why we use PCMs? Recently, interest in PVTs integrated with PCM has increased because we can obtain regular and more stable thermal energy by PVT PCM systems, and we can store the energy by PCM. It's a good option to integrate thermal energy storage material with PVT systems to obtain thermal regimes. The aim of the study is to investigate optimum flow rate for maximum outlet fluid temperature. As we all know, flow rate is one of the most important operation parameters for PVT PCM system for all thermal systems. Furthermore, outlet temperatures is a measurable parameter, and we can measure easily in our experiments, in practice. So it will provide, it could provide great convenience in practice. For the first time in the literature, optimum flow rate for maximum outlet temperature is investigated by ANSYS in this study. For the system description in the figures, we can see PVT PCM system established and tested in Uşak University by a TÜBİTAK project. On the left, PVT PCM system and measurement devices can be seen. On the right, we can see the placement of thermocouples on the copper plate of PVT. In the experiments, we used 13 K-type thermocouples to measure PCM layer temperatures. We chosen paraffin as PCM. Working fluid was tap water for the PVT system. we can see the experimental design. We have a meteorological station in our department. We measured inlet and outlet temperatures, electrical parameters, ambient temperatures, temperatures on PVT surface, wind speed, etc. By the way, I would like to mention about our energy laboratory shortly. We can also produce our own PV panels by a semi-manual lamination machine. And I would like to show our production. And we had a certification for own PV panel from Turkish Standards Institution. This certificate belongs to our first production. If you need some specific design for your PV projects, please don't hesitate to contact me. Let's continue the subject. Top left figure shows the layers of PVT PCM. The layers from top to bottom are listed: glass, ethyl vinyl acetate, solar cell, ethyl vinyl acetate, copper pipe, copper plate, PCM, plastic backing, insulation material, and casing. PVT PCM was tested experimentally. In these figures, we can see the variation of inlet and outlet temperatures, ambient temperatures, and solar radiation on PVT surface during the day at the different flow rates. These figures show us the temperature distribution from PCM layer at different flow rates during the day. As I mentioned before, we placed 13 thermocouples on copper plate of the PVT systems. From the figures, PCM temperature increased with increasing flow rates. And a modeling is needed to reveal the optimum flow rate for the most efficient heat transfer. PVT PCM system experimental tested was modeled by ANSYS. To validate the model, we compared measured outlet temperatures to estimate outlet temperatures. We obtained a relatively high determination coefficient between these parameters. After the validation, we investigated the variation outlet temperatures by flow rate. In practice, we want hot water from PVT systems. For this reason, in determining the optimum flow rate, the strategy of reaching maximum outlet water temperature was followed. Flow rate values were selected from 13 to 45 liter per hour, and the highest outlet temperature was achieved for 19 liter per hour. Yes. Sorry. And now conclusion. We also modeled temperature contour, pressure contour, and velocity streamline of PVT PCM system at optimum flow rate. And now conclusion, from the analysis, optimum flow rate was found as 19 liter per hour. For the conditions described here, 15 and 21 liter per hour flow rates can be selected as the ideal flow rate for paraffin in practice. PCM are favorite materials to thermal storage for PVT systems, especially for the last decade. However, I would like to mention some important, even crucial challenges for PCM. PV surface temperature could rise above 70 Celsius degrees, and we choose paraffin and its melting temperature was 56 Celsius degree. However, experiments have shown that paraffin has not completely melted. For future work, it should be investigated the optimum melting temperature of PCM for PVT application for different metallurgical location. And the biggest problem to be overcome here is the relatively lower thermal conductivity of the PCM. Thermal conductivity of PCMs should be increased to enhance the heat transfer mechanism for PVT systems. Experimental studies have shown that PCMs such as paraffin some disadvantages in PVT applications. For example, the necessity to use PCM with different melting temperature for each climate zone is an uncontrollable challenge in terms of the production and marketing of such PVT systems. Another challenge, the discharge time of PCMs is not compatible with the economic life of PV systems, and they will have to be replaced after a certain period of time. A flexible design should be made against the volume changes that occur during the melting freezing period, and the PV systems should not be damaged mechanically. Another challenge, the use of PCM causes a considerable increase in the weight of PV system with an average weight of 20 kilogram, and PVT PCM applications should be applied by considering the building static load resistance. The last challenge that I want to mention, since most of the PCM have chemical toxic effects, care should be taken to keep the utility water clean in PVT application. To prevent the leakage, it's recommended to use suitable working fluids and double-walled heat exchangers. Thank you for your attention.
And thank you for your presentation. Okay. There is a
Is there any question?
Yeah, there is a question. They wanted to know about what will be effect on life of a PV module due to extra loading of water mass and PCM mass.
It causes increasing the static load on the roof, and very heavy. We obtained very heavy PVT systems, about 40 kilograms per module, increasing static load on the roof of the building. It's very bad for building integrated photovoltaic systems. Thank you.
Thank you. Is there also any other plans in order to increase the conductivity in the paraffin materials that you're using in the PV panels, such as some mechanical designs? Because you cannot change the property of the PCM material, right? So you need a mechanical design.
Actually, there are many studies to enhance thermal conductivity of PCM by adding some nanoparticles, some for example aluminum, graphites, etc. nanoparticles. By adding, we can increase thermal conductivity by adding additional particles to PCM. Actually, we have tried another material, heat storage material. We had a university industry project, TÜBA project, and we used natural zeolite plates for PVT systems to heat for thermal storage and to obtain a regular thermal regime. We gave up fast change material because of these challenges, and we had tried natural zeolite plates. We produced natural zeolite plates to integrate PVT systems, actually. Thank you.
Okay, thank you very much for your presentation.
Thank you for your efforts.
Okay, thanks. So it's 7:45. There is supposed to be another presentation titled Exergy Analysis of a Steam Power Plant at Full and Partial Load Conditions by Mr. Azubuike, Njoku, and Ekechukwu. But are they here? Any of them? I can't see a...
Dear moderator, they are not here yet. We can move on next one when they be here, and I will transfer them to the panelist list, okay?
So, okay, they're not here. The next presentation is technological assessment of a solar PV collector for freshwater cooling and electricity by Mr. Khalid. If he is here, we can start the next presentation. Yes, he is here. Okay. Faruk, you can,
yeah. Can you hear me?
The screen is here. I can hear, we can hear you all. The screen is yours.
Okay, just wait a moment. Fix this here. Okay, so thank you very much, Mr. Chair, for giving me an opportunity to present my work. And myself, Farooq, and my work is basically a technological assessment of a solar PV collector for freshwater cooling and electricity. So what basically we have tried to do in this work is that we design a system based on PV collector that can give us the electricity, the fresh water, and the cooling by using a technology called as a freezing and defreezing technology. So I would like to move my presentation in the following way. That first I will introduce why we need such type of systems and what is the need for this, and then what is the motivation behind this work, and then some key goals or the objective of this work, and what type of system I have analyzed, and then it's a system analysis using the principles of thermodynamics. That is the first law and the second law, and some results. And at the last, I would like to conclude my presentation. So as we all know that when we go for the things, we say that energy is the key to development for any country, for any nation, whatever we have. So it's very important to have energy, but the key thing is that this energy need to be obtained or attained in a sustainable way. And mostly, as we see that most of the world is getting this energy from the fossil fuels because it is considered as a primary energy source. And however, it has some limitations, and those limitations are that it is going to be end later or sooner someday. Another thing is that it has a very high impact on the environment, which can be seen as we see from the table that there are the CO2 emissions worldwide in the year 2018. And as we can see, around 99% of those come from the fossil fuels. And on the left-hand side of the graph, we see that this energy demand from the year 1990 just keep increasing. So, and up to 2018, this keep increasing, and we see that further it is going to be increased. So another issue that is I will to dwell on that and see that this is the water demand of the world. So we see in the year increasing to 4 trillion million in the year 2014. So this is the latest data which is available, but I'm pretty sure that it is going to be increased in the nearby future because of the agriculture advancement and so many things. So the demand for the fresh water, the immense pressure on the scientists or the researchers worldwide to find sustainable way for producing fresh water and electricity in a benign and a sustainable manner. So there are many ways in which one can produce fresh water by using different technologies. So such technologies use different energy methods. Some of them are electricity driven, some of them are thermal driven, or we can say the heat driven, and some of them are the combination of those. So in this regard, what we have choose is basically the freezing technology, because it is good for water input for salinity around 37,000 ppm, and we can get water of fresh water of around 200 ppm, which is good for the domestic purposes and for agriculture purposes. So in a nutshell, as a factor of three things, that is the population, and then the consumption of the energy the persons are using, and the environmental impact of the unit of those resources from where this energy comes from. So we can see that the two factors are not something that we can curb in a day or in a fortnight. So the only thing that we can readily overcome or use is that how to reduce this environmental impact of the unit consumption. So this can be done by employing our technology or moving our technology from fossil fuel based to the renewable energy. As we can see in this graph, the emissions of the different technologies being given, and we see that the renewable energy comes as one of the promising renewable energy solution. However, we need to harness this in much better way, whatever the available options we have. So the challenges that associated with the renewable energy can be that it has an intermittent and the fluctuating nature, and we need to make these technologies more and more efficient. And some initial they are little bit have higher initial or the capital cost, but that can be overcome by giving the subsidy from the government and other policy makers. So the potential solutions could be that we integrate one or two more sources. Another thing that could be, instead of placing, let's say, PV or those things only for electricity or that, we can use them for cogeneration, multi-generation, and other purposes. So the motivation behind it was that the demand for the energy and the fresh water was increasing, and the environmental degradation related to that use was also been there, and the rise in the living standard is keep increasing day by day. So there is an immediate need for a sustainable and clean energy systems that will give us the electricity, cooling, and the fresh water. So the key goals of the work are that we need to design a system that can give us a cooling, electric power, and fresh water, and mainly run by solar energy in the form of the photovoltaic collectors. And then to employ a technology that is called as a freezing defreezing technology, that is based on the vapor compression cycle by a conventional refrigerator, that is the fluid we use in the conventional refrigerator, that is R134A. And then to finally analyze this design system via the principle of thermodynamics to see what energy and efficiencies we are getting. So our system looks a very simple one, in that we have a solar PV collector, and then to this electricity is being goes to the vapor compression cycle, where it is being used to run the evaporator, and some portion of the cooling from the evaporator is being used to freeze the brackish water or the saline water, and then this is being further that water is being defreezed by using the heat from the PV panels. So basically we are getting the fresh water out of it. So in order to start the analysis, we make some reasonable assumptions. Those assumptions that the potential kinetic energy changes were negligible, and the compressor and the pumps, we assume that those are the adiabatic ones, and the pressure loss in the heat exchangers and the pipelines, we assume that to be negligible because of the size of the system what we consider. And we assume when the system has started and achieve the steady state, we do its analysis. So we assume that the system behave in a steady state fashion, that is no effect of the time or the dynamics of the system is being considered in this. So after that, a general balance equation has been written, that is by using the mass, energy, and entropy and exergy balances. So in order to analyze the PV system, the most important thing is its cell temperature, because the performance of the CV basically greatly depend upon the cell temperature. So this cell temperature is being calculated by using a method that is given by Duffy and Bakke in the year 1982. So we use that. And then the energetic performance of the overall systems is being calculated by writing the principles of energy and exergy efficiencies. And we know that since our system is producing three things, those were the cooling, fresh water, and the network. So we analyze and we write them based on that. So after applying the principle of thermodynamics, the isentropic efficiency of the compressor of our compressor was found to be around 75%, and the evaporator temperature, what we considered in our analysis, was around minus 5 degrees Celsius, that is around 268 Kelvin. And then the COP of our cycle was found to be around 2.6, and this system can give us a cooling load of around 6 kilowatt, which is sufficient for any house or anything. And then the power consumed by this compressor of this vapor compression cycle was around 6 kilowatt. So basically this compressor, this vapor compression cycle was able to produce the cooling as well as the amount of cooling or this being required to freeze the water. So the amount of electricity or the amount of cooling effect that is required to freeze the water was 9 kilowatt. And once we find the performance of the overall system, we found that the energy efficiency of the system was around 19%. However, the exergy efficiency was around 7.5%. And after that, we see how the performance of this system changes with the effect of system. And we found that once the outdoor temperature increases, the performance of the overall systems decreases. The reason is primarily that with the increase in the ambient temperature, the performance of the PV decreases. So eventually, which is being reflected on the performance of the overall system. And similarly, we see that what happened if we increase the evaporator temperature. So if the cooling or the temperature was increased from -10 to 5 degrees Celsius, we found that the performance of the system increases. The reason is that we are basically decreasing the evaporated temperature. So we don't need much more cooling in this case. And then we see what will happen to our system if we increases the demand of the fresh water. And we see that once the fresh water demand has been increases, the performance of the system is being decreases because the fresh water is a commodity, we can see in this way. So at last, to conclude, we see that our solar operated hydrogenation system based on PV is being designed that is being able to provide the cooling, electricity, and fresh water. And this system has been technologically been evaluated with the principles of thermodynamics via exergy and energy analysis. And our result shows that a cooling effect of around 6 kilowatt can be achieved with a fresh water rate of 54 kilogram per hour under such design conditions. And our efficiencies was around 92% for the overall system, and exergy was around 7.5. And these types of findings in the current research or such type of system will help the investigator worldwide to design much more efficient systems for the remote areas and as well as for greenhouses, as what was discussing. So such types of systems can be coupled or being used for those water and cooling and all other things. So such types of systems can be utilized there. So with this, I would like to conclude my presentation and thank you very much. If anyone has any questions, he or she may ask. So following other references through which I have been. So,
okay.
Thank you.
Thank you very much for your presentation, Dr. Khalid. Is there any questions for Dr. Khalid? Okay, there are no questions. Thank you very much for your presentation.
Thank you.
Then I'd like to announce the next presentation by Siddhar Reddy and Tiwari, titled Mathematical Modeling of Adsorption Isotherms for Porous with Actual Dispersion Model. Is the
Good morning, sir.
Here?
Am I audible?
Yes.
Yes.
Okay. Okay, the screen is yours.
Yes, sir. Thank you. Good morning, everyone. Myself, Siddhar Reddy Manikandan. I'm from India, doing my PhD under Dr. Sumit Tiwari in the Department of Mechanical Engineering, Shivanada University. Presently, we are working on modeling the adsorption process using axial dispersion model. In our work, presentation, we will be covering the different basic types of adsorption and different types of desiccants and methods available for regeneration and mathematical modeling of adsorption system and conclusion. Generally, adsorption cooling systems are based the refrigerant system used for cooling purpose using the adsorbent bits which adsorb and desorb the refrigerant. In general, it's due to the surface phenomenon without any chemical change. In general, increasing in the adsorption in pore area of adsorbent increases the cooling effect. The adsorption process can be divided into two types, which is physical adsorption and chemical adsorption. In physical adsorption, the adsorption process solely takes place due to the weak van der Waals force. Similarly, in case of chemical adsorption, it is due to the chemical forces between and short covalent bond between on the surface. These are the simple components of adsorption cooling system, in which it consists of solid adsorbent bed, condenser, evaporator, and expansion valve. Generally, the simple adsorption cycle operates between two constant pressure and one maximum and one minimum concentration level. In general, it has 4 steps, which is preheating, desorption, pre-cooling, and adsorption process. In preheating process, the hot water is supplied to the adsorber bed in which the pressure rises. When the pressure of the adsorbed bed reaches equals to the condenser pressure, then the valve to the condenser opens. Similarly, the temperature of the hot fluid flowing through adsorber is increased such a way that the evaporation of adsorbed bed takes place. So the evaporated adsorbent goes to condenser and condenses there. In pre-cooling process, the hot adsorbent bed is cooled by passing through the cooling water, in which the pressure level reaches the evaporator pressure. At that stage, the valve between the evaporator and adsorber opens, and again the cyclic process continues. There are many advantages of adsorption process. They are like it's noise-free and its ability to work in mobile condition. Different range of adsorbents can be used, and it can be used for varying temperature heat source, and no dangerous chemicals are used. Similarly, generally we will use water as a refrigerant, zero ozone depletion and potential refrigerant, less maintenance. Even the disadvantages of adsorption systems are the COP is very less and the discontinuous cooling is possible. So we need many beds to give continuous cooling. Similarly, there will be pure heat and mass transfer in the adsorbent beds. Similarly, the system requires large space and it's not economical yet, and the vacuum tightness of container is needed. These are the different desiccants available, which are generally the desiccants are the materials which have high affinity towards the water molecules. They can be classified as solid and liquid desiccants. Generally, the features of good desiccant is it should have high adsorption capacity and also for all ranges of relative humidity. And the one of the major advantages should be it should be regenerated at low temperature. In our case, we have conducted mathematical modeling in 2 steps. In first step, we are using axial dispersion model to study the concentration of adsorbent on the adsorbent bed. In second step, we are doing the same analysis using the Darcy law and heat transfer to porous medium to study the velocity, pressure, and heat transfer in the adsorbent bed. So in first, as initialization, we have given all the properties of adsorbent and adsorbent, and similarly we meshed it to fine mesh, and in results we studied the adsorbent concentration, velocity distribution, temperature, and different isotherms. These are the governing equations which we use, which is the axial dispersion model combined with the linear driving force model, in which the linear driving force model, the Q star is calculated using different isotherms, which are namely generally available isotherms like Langmuir isotherms, Freundlich isotherms, and the Cpsc isotherm, which is the combination of both Langmuir and Freundlich isotherm. In general, in COMSOL multiphysics, we have option like PDE model, in which we can discretize the equation in terms of general PDE coefficient form of PDE, and we can input our equations. These are the results obtained from the analysis, in which the Langmuir adsorption isotherms gives accurate results compared to the other adsorption isotherms, but the only problem we are facing is an accuracy. So in next step, we will be trying with a different integration like hybrid finite element method and all. So these are the results for the second step, in which we have studied the temperature distribution and velocity distribution in the desiccant bed. In general, in case of temperature, it's gradually increases with respect to time, and it reaches maximum, and after that it reaches the equilibrium and it attacks the same temperature in the bed. Similarly, in velocity also, when you give the velocity, gradually increases with the time and reaches the maximum, and reaches an equilibrium. These are the conclusion. Actually, we have only done with 3 different isotherms. In future, we are planning to combine different adsorption isotherms like Dubin-Askarkov equation and polynomial theory and all. Similarly, we will be experimentally going for the adsorption disruption process, and also we are planning to integrate different energy sources for regeneration process. These are the references we have gone through. So thank you. Any questions? Thank you, sir.
Thank you, Manigandan, for this very fast presentation. Okay, any questions from the attendees and the panelists? Okay, there are no questions, and this is the last presentation. Actually, I think one of the presenters...
He's online now.
Yeah.
The last presenter is online now.
The third presenter, the fourth presenter, Mr. Azubike is here now. Mr. Azubike, can you hear us?
Yes, I can hear you very well, sir.
Okay. Okay, good. Okay. Can you share your screen with us, please? Okay, very good. Now we are going to listen to Mr. Azubike and his colleagues titled Exergy Analysis of a Steam Power Plant at Full and Partial Load Conditions. The screen is yours.
All right. Thank you, everyone, and apologies for making it up in the due time. My name is Zubiki Uchenda, and I'm here to present a title or a study, Exergy Analysis of a Steam Power Plant at Full and Partial Load Conditions. My co-authors are Ebu Uzo, Njoko, and Ekechukwu. We are in Applied Renewable and Sustainable Energy Research Group in the Department of Mechanical Engineering, University of Nigeria, and Ebin Plants, Lagos State, Nigeria. Energy, as we all know, is everything existing in the world is either energy or matter, and everything that happens utilizes energy. According to US Department of Energy, consumption of this energy would grow by 71% between 2003 and 2030. And this figure will double between 2000 and 2040. Fossil fuel contributes about 85% of the world's energy used in generating electricity in thermal power plants. And due to the inefficiency of these installed power plants, exergy analysis are frequently required for the plant's improvement. The usefulness of exergy analysis are numerous, such as improving the power plants, economic and environmental evaluations, better understanding of energy conservation and crisis, and also it helps in optimizing of these power plants. Now let's take brief literature review for this study. Dang et al. Carried out exergy analysis on the 600 megawatt steam power plant for 2 different loads. They carried out on the design load, which is 100% load, and off load on 70% load. Their results show that decreasing the load from the design load decreases the exergetic efficiency of the plant. Another researchers carried out such studies on a 4.2 megawatts gas turbine plant for varied load of 50% less than the design load. The results show that energy destruction in the components of the plant increases from the 50% offload to full load, except for the compressor. Now let's discuss the aim and objectives of this study. So this aim, our study aims to carry out energy analysis of partial offloads of a 220 megawatt steam power plant, which is very the design operating load to 25 we studied or we discovered that our aim, our objective is just to find the energy destruction in the components and in the overall plants for both the design and the partial operating loads. Or we also find the performance of the individual components and the overall plants at the partial operating loads. Now, this is our study. It's a flow diagram of a wind 220 megawatt steam power plant, which is located in Lagos, Nigeria here. So as you can see from this diagram, we have our boiler, we have our turbine section. This is a high pressure turbine, this is intermediate pressure turbine, these are low pressure turbine, and this is our and this is our generator, this is our feed water pump, high pressure heater 5, high pressure heater 6, and pipes connecting these lines. Now, superheated steam from this boiler is fed into this HPT, which is a high pressure turbine, which is a high turbo turbine, which is in exiting, it is reheated and fed to our intermediate pressure turbine, and then fed to the low pressure turbine. Now we have extracted steam. We have extracted steam to a high pressure heater 6. We also extracted steam to heater 6, 5, and generator. We also to the low, from the low pressure turbine to the low pressure heaters. Okay, this is a description of what I just described, so there's no need to go through it again. Now, the data. Okay. Yes, so these are the key parameters we obtain from the varying load. These are the key parameters as shown in table 1. So on a 25 load, we obtain the generator power is 55 megawatts. On 50% load, the generator power is on 110 megawatts. On 75%, 165. On 100%, which is our design load, is on 25 megawatts. So these are mass flow rate we obtain from the plant. This is the fuel gas flow rates, and this is the heat rate. These are our higher heating value for the plant. Sorry, a minute, please. A minute, please. I'm using the wrong file for this. Apologies to everyone, please.
Mr. Azubike, I'm sorry for the interruption.
Apologies, please. Apologies, please. Apologies, please.
It's okay. I just want to inform you about your connection. Could you continue without your camera because people cannot hear your voice?
Okay, I should continue with my camera.
Yes, without camera. That's why you should continue without camera to show your name and to show your presentation.
My camera, right?
Okay.
Can you hear me?
Yes, hello? We hear you now.
Apologies to everyone, please. Now, this is the descriptive pictorials. I hope you can still hear me. These are descriptive pictorials of the various components. We actually studied on the exergy. Hello? Hello?
We hear you. We hear you. You can
Okay.
continue.
Okay.
It's okay.
Okay. All right. These are the descriptive pictorials of the various components of the plant. And this is the components, and this is the exergy destruction. And this is exergetic efficiency, what we actually focused on. So this is the, for instance, we have the condensate pump, this is PI, and this is the exergy destruction. And this exergy destruction is given in terms of fuel exergy and product exergy. So this is the fuel exergy, that's the expense to and these are products over the input. Also, drain cooler is something for the plant. Use of 25, 50%, 75% of 10. The pressure, temperature, enthalpy, mass of the flow points, components, that's I described before. These are the for the different loads. The one is very, very low. And hello.
Mr. Azubike, share your screen again, please. It's almost impossible to hear your voice. Do not open your cam and keep going from where you're left.
Continue. Yeah, it's very calm. Maybe it's as a result of the network. Can you hear me? Hello? Hello? Can you hear my
Keep
voice?
going, keep going.
Can you hear my voice now? Should I continue? Hello?
Yes, keep going, please.
Okay.
Hello.
Yes.
Mr. Azubike, I can hear you, but we cannot see anything on the screen.
And I'm sharing my screen right away. Can you see anything on my screen?
Only one page. There is a connection problem, I'm guessing.
Can you see?
So just go to your results and discussion very fastly, please, and
Okay.
try to finish, because this, there is a continuous connection problem and it's impossible to hear. So just provide your results and your conclusions, please.
Okay. Can you see my screen right away?
Yes.
My screen?
Oh, yeah.
Okay. So I'm discussing the results. I hope you can see my screen now. Hello?
Yes, we
Hello?
can.
Okay. These are the few results. These are energy destruction on the components. And this is for the condensate pump. We found out that the condensate pump has low energy destruction compared to the feed water pump. And we can see from here that the energy destruction at 25% load is higher than the energy destruction in 50% load. For the drain cooler, we discovered that the energy destruction decreases as the load decreases. Now, for the low pressure heaters, we found out that the energy destruction decreases as the load decreases. As you can see that the low pressure heater has the highest energy destruction compared to low pressure 2 and 3. And low pressure heater 3 has higher energy destruction compared to low pressure heater 2. Now, this is for the high pressure heaters. This is the deaerator, high pressure heater 6, 5, and high pressure heater 6. As you can see that the high pressure heater 5 has higher energy destruction compared to high heater 6. And you can also see that the energy destruction decreases as the load decreases. Now for the boiler, high pressure heat turbine, high pressure intermediate pressure turbine, low pressure turbine, and the condenser, we can see that the boiler contributes or has higher energy destruction when compared to all components, as you can see. And also the energy destruction decreases as the load decreases. Now we found out that in the high pressure heater, in the high pressure turbine, at 50% load, the energy destruction was highest compared to that of 25%, 75%, and at the design load, which is 100%. Now, on the intermediate pressure heater, the energy destruction decreases as the load decreases. Likewise for the low pressure heaters and for the condenser. Now, let's discuss the exergetic efficiency for the various components. Now, we found out that the energy destruction in the condensing pump was very small. So, therefore, we have high exergetic efficiency, as you can see from figure 6. And you can see that for the partial load, the exergetic efficiency was higher than the design load. Now, in the feed water pump, we discovered that at 50% load, the exergetic efficiency was highest compared to the design load, 75% load, and the 25% load. Now, also on the drain cooler, we discovered that at 25% load, the exergetic efficiency of the drain cooler was highest when compared to the design load, 75% load, and the least, which is the 50% load. Now, for the low pressure heaters, we discovered that the low pressure heater 2 and 3 are high in terms of exergetic efficiency when compared to the 3 low pressure heaters. As you can see, we discovered that at 50% load, the exergetic efficiency was higher than that of 100%, which is the design load. Now at low pressure heater 2, we discovered that the design load has higher exergetic efficiency when compared to the partial loads. Now, at low pressure heater 3, we also discovered that the partial load, the design load has higher aesthetic efficiency when compared to the partial loads.
Hello. Hello. Mr. Azubike, we cannot hear your voice. Anyway, it has been very long, and this presentation, the connection problems is okay. Mr. Azubike, the presenter is offline. Anyway, I'd like to finish this session. And I thank all the panelists and the presenters for their works and their time, and also the attendees for attending this session. All right, the session is finished now. Thank you.
I think it's time now. Hello, welcome to the Energy and Environment 2 session in TÜBA World Conference on Energy Science and Technology. I'm Isentropic from University and will be your host for this session. I see that we have very interesting presentations. We'll first start with Anıl Erdoğan.
Yes.
Do I have to give you something to, can you share your screen?
Okay.
The presentation is entitled 0D Parallel Circuit Modeling of Solid Oxide Fuel Cell by Anıl Erdoğan, Ayfer Can İnce, and Can Özgür Çolpan.
Okay, thank you. Can you see my screen?
Yes.
Okay, thank you. Good morning, dear session chair and dear participants. As I introduce myself, my name is Anıl Erdoğan. I'm PhD student at Mechanical Engineering Department of 9 Eylül University. I will present our study, and this study is performed with my friend Mr. İnce from Gebze Technical University and our supervisor Professor Çolpan from 9 Eylül University. My presentation outlines introduction. I will give brief information about solid oxide fuel cells and then parallel circuit approach for solid oxide fuel cell, which includes modeling equations and solution algorithm, and then validation and parametric study results I present, and finally conclusion and future works. Solid oxide fuel cells are high temperature fuel cell which operates between 500 degrees Celsius and 1000 degrees Celsius. Application areas are stationary power and heat generation, transportation applications, and portable applications. There are some advantages for this type of fuel cell, which are no need for previous metal-based electrocatalysts, fuel flexibility. There are a lot of fluid as a fuel. For example, hydrogen, carbon monoxide, methane, biomass-produced gas, ammonia, and hydrogen sulfide, etc. And internal reforming and good thermal integration with other systems, such as Rankine cycle, organic Rankine cycle, Brayton cycle, and gas turbine systems. There are some disadvantages for this type of fuel cells. Degradation due to the carbon deposition and sulfur poisoning, challenges with construction and durability, especially mechanical strength. This figure shows the illustration of solid oxide fuel cell with anode recirculation. The gas mixtures enters the anode side, which includes methane, carbon monoxide, hydrogen, carbon dioxide, and nitrogen. Enters the fuel channel. At this point, methane and carbon monoxide transforms hydrogen-rich gas with steam methane reforming and water gas shifting reactions. And then at the anode side, hydrogen and carbon monoxide oxidize with producing of water and carbon dioxide. And the cathode side, oxygen transforms oxygen ion that travels cathode to anode side. Here is the table for input parameters for the modeling study. The input parameters includes anode side species, cathode side species, and operational parameters, pressure, temperature, current density, exchange current density for both sides, and fluid utilization ratios. And geometrical parameters that include active surface area and thicknesses of each component, such as anode, electrolyte, and cathode. This figure illustrates that the equivalent circuit of the solid oxide fuel cells. as mentioned earlier, there are two electrochemical reactions at the anode side, which are hydrogen oxidation and carbon monoxide oxidation. Thus, these oxidation reactions can be handled separately. For this reason, hydrogen side, which includes Nernst voltage and polarization resistance, is here. Ohmic, activation and concentration, and cell voltage calculations. For the same for carbon monoxide side, Nernst voltage, ohmic, activation, concentration, and cell voltage. Considering the parallel circuit approach, the cell voltage due to the hydrogen oxidation is here. The cell voltage for hydrogen oxidation is equal to carbon monoxide oxidation according to parallel circuit rule. And carbon monoxide...
Bilmiyorum bakalım.
Sorry?
Becerirsek becerdik, becermesek bir şey yok.
Pardon, it's not... yeah. You can continue.
Okay, thank you. Current density for carbon monoxide oxidation can be found using these formulations. Beta is the surface ratio. This figure shows the solution algorithm of our model. There are two XO blocks calculating the output parameters. The first SO block is calculates the anode exit side conditions, and second SO block is the calculates for cell voltage, power produced by solid oxide fuel cell, and oxygen utilization, etc. Validation study. This figure shows the validation study found compared with experimental results found from the literature. The validation results indicated that the cell voltage and power density values obtained from the model are close to experimental results, and maximum errors for cell voltage values is 6.34%, whereas for power density the maximum error is 5.44%. As parametric study, the effect of current density on the cell voltage and power produced by SOFC according to electrolyte thicknesses. As the current density increases, the cell voltage decreases for all electrolyte thickness values due to the polarizations. On the other hand, as the current density increases, the power produced by SOFC increases up to a certain value and then decreases. And the parametric study results indicates that as the electrolyte thicknesses increases, the operating range of current density values decreases. As conclusions, the cell voltage and power density values are very agreeable to those of experimental study under the same current density. When the electrolyte thickness increases from 10 micrometer to 40 micrometer, the cell voltage is reduced by 41.24%, whereas the electrolyte thickness is changed from 10 micrometer to 40 micrometer, the power decreases by 39.96%. As the future works, exergy analysis will be done for the study, and pressure drop phenomenon, which based on fluid mechanics principle, will be added to the model. Thank you for listening.
Thank you. You used your time very well.
Okay.
We can ask questions from the Q&A panel on the screen. Before our listeners ask a question, I have quite a lot actually myself, because fuel cells are not really my area of expertise, but we hear that they are very important in the future. And what was the most difficult challenge you faced in your study?
In this type of fuel cells operates at high temperatures, so that there are some challenges with this type of fuel cells. For example, durability, of course, and mechanical strength, for example.
Oh, so these are challenges for future use.
Yes.
And what was the most difficult thing you faced in your study?
Yes.
Oh, so when will we see your fuel cell in the market?
Okay, maybe.
So if there are not any further questions, we can go to the next presentation. I see that Kamil Kaygusuz is here. No, I cannot see. Is Kamil Kaygusuz here? Okay, if or when he comes, then we can start his presentation then. And I think he will also present the next paper, although I see Ali Sarı is the presenter. I also cannot see him here at the moment. So Yargı is, yes, Önder Yargı is here.
Yes. Hello, everyone. Do you hear?
Yes, we can hear you. Hello.
Hello. Let me introduce myself before my speech. Thank you, by the way. My name is Önder Yargı from Yıldız Technical University, Department of Physics. And then let me share my screen, please.
Yes, his speech is entitled Asymmetric and Symmetric Coin Cell Supercapacitors by the Position of Graphene for Energy Storage Applications.
Yeah, thank you. Yeah, as I said before, I'm from the Department of Physics at Yıldız Technical University. I'm also founder of Aidon's technology company based on energy storage. We have different types of supercapacitor that we are developing. And today I'm going to talk about some supercapacitors for energy storage applications. Yes, supercapacitors are an energy storage device. They also have high power densities. Supercapacitors have very thin electrode surface and can be charged and discharged very quickly. And they can be in different shape structures as in the picture. They are charged and discharged very fast thanks to their very thin electrode structures. They create high power densities thanks to their quick discharge process. While they don't have high energy densities like batteries, they have much higher power densities than batteries, which allows them to be used in all areas where high power is needed. If a long-lasting energy is needed, batteries should be used instead of supercapacitors. However, if high power is needed, a supercapacitor should be used then. Battery and supercapacitors can be used together, that is, in a hybrid structure when both energy is needed again. Supercaps are not only as an energy storage devices, but also as an energy regulators. In our daily life, It can be used in many areas, such as photograph flashes, UPS, LED, some hand tools, etc. In industrial applications, as it can be seen, wind turbines, solar panels, electrical cars, trains, and buses are some of them. Yes, the picture on the upper right shows the use of supercapacitors according to the potential range needed. And the picture on the lower right shows the areas of use in the industrial applications. In the picture on the left, it is seen that supercapacitors are mostly used at values between 50 and 100, between 10 and 25 voltage. It's clearly seen that the most used sector is the automotive sector. Yes, as I said before, we have different types of supercapacitors that we are developing. One of them is solid state supercapacitor, and the other one is interdigit supercapacitor. And currently we are developing conventional supercapacitor, including liquid type supercapacitor. This picture shows an experimental part of the production of the last supercapacitor that we have produced. Figure A shows the picture of the porous nickel electrode used in the supercapacitor. And in figure B, a porous acrylamide, which we synthesized to be used as a separator. In figure C, the cell where the supercapacitor is placed and analyzers are applied. In our last study, graphene was deposited onto porous nickel electrodes by electrochemically. Separator was placed between the cathode and anode electrodes. And then we waited for a while with ionic liquid for embedding process placed inside. We arranged and closed the steel cases as in the picture and prepared CR2032 supercapacitor. 3 different CR2032 coin cell type supercapacitor were developed based on deposition of graphene on nickel and copper foam as 2 symmetric and 1 asymmetric with 3-fluorometallosulfate as a redox active electrolyte to achieve homogeneous electrochemical deposition of graphene on porous nickel foam and copper foam electrodes. Lithium perchloride electrolyte was preferred. This is 2 brands by supercapacitors. On the left side, most of us may know that Eaton is a well-known brand in the world about supercapacitor. Adams, our company, and we are still developing supercapacitor. As can be seen that max voltage by Adams company, 3.2 voltage, by Eaton, 2.5 and 2.75 voltage. Separator process by Adams Technology, integrated system, by Eaton, external process. By Eaton, capacitance value, just 1 farad, by Adams company, 2 farad, at the same properties. As for the price, by Adams Technology, it's only just $1. By Eaton, it changed $10 and $20. Yes, we have different type of supercapacitor, but the last supercapacitors that we are developing was graphene supercapacitors. Graphene supercapacitor because thin layer of pure carbon tightly packed and bonded together in a hexagonal honeycomb lattice. Thinnest compound known to man at 1 atom thick, as well as the best known conductor, amazing strength and light absorption, ecologically friendly and sustainable as carbon is widespread in nature and part of the human body. Graphene is often suggested as a replacement for activated carbon in supercapacitors. The surface area is one of the limitations of capacitance, and a higher surface area means a better electrostatic charge storage. In addition, graphene-based supercapacitors will utilize its lightweight nature, elastic properties, and mechanical strength. A graphene supercapacitor is said to store almost as much energy as a lithium-ion battery. This picture shows copper foam covered by graphene homogeneously. And this is capacitor retention for CR2032 type supercapacitor for the different type. Figure A, the symmetric supercapacitor, and figure B, asymmetric supercapacitor. As can be seen that after 5,000 charge and discharge process, capacitor retention doesn't change, and it is almost 100%. Yes, if you have graphene-based supercapacitor, you can also use it alternative to a scooter battery. For this reason, you need 12 pieces, 500 farad capacitance value, and 2.7 voltage, and the package size should be 10 and 24 centimeter. Yes, if you use it with batteries, you need, for above example, 30 pieces lithium ion. For below example, you need 30 pieces lithium ion, but 6 hours for below, 5 hours for above the charging time with 2 ampere and 3 ampere. Requirements in general, 36 volts with energy 250 and 600 watt you need. Conclusions. In this study, graphene in lithium perchlorate on nickel and copper foams was deposited electrochemically. In addition, a flexible and nanostructured polyacrylamide hydrogel has been synthesized, which allows a significant ion transfer. The conclusions obtained from this study can be summarized as follows. From the electrodes prepared by electrochemical method, 3 different CR2032 coin cell supercapacitors were designed and evaluated. The capacitance, energy, and power densities obtained have been found to be compatible with the literature. Capacitor retention has exhibited excellent results in 2 symmetrical and asymmetrical coin cell, and no loss has been observed up to 5,000 charge-discharge cycles. While it's not possible to reach high currents for copper-based supercapacitors, it is possible to operate up to 5 milliampere with a nickel-based supercapacitor. Polyacrylamide, hydrogel separator, and TFMS electrolyte have formed a very compatible structure, while nanoporous polyacrylamide hydrogel degrades in 6 molar potassium hydroxide. It can be used for a long time without degradation in TFMS. Yes, it was the end. Thank you for listening. If you have any question.
Mr. Ayça, do you?
Oh, we can hear you, Professor Kaygısız.
Yes, yes, I am Professor Kaygısız.
Oh, hello.
All time Kaygısız.
Hello, sir. We had some technical problems.
Yes, yes.
Now, Professor Yargı was just came to the end of his presentation.
Yes.
If there are not any other questions I would like to ask. You said that you have a firm that is related to your research.
Yeah.
And can you
sure.
tell us something how this research is related to it?
Thank you for asking. Yes, our company is based on energy storage, which is called Addons Technology Company. We are developing 3 different type of supercapacitor currently. The first one is solid state supercapacitors. Solid state means that when you use electrodes and separator, you don't need any liquid from outside, which supplies high power and more durable supercapacitor to higher current and voltage. And the other one is interdigit type supercapacitor. This is you can imagine a flat surface covered by a material like graphene. After this, you can apply a laser to give a pattern, different pattern. This pattern supplies a different type of energy and powers, this kind of type. And the last one we are currently developing, the conventional supercapacitor, which means after preparing your electrodes separator, you are adding some external liquid to give the ions transfer between the electrodes. This type supercapacitors. We have this company is just for 2 years, but we are developing, of course. Yeah, I can say this.
It's very nice to see the university and company together, so that the research will come to our lives more rapidly, I hope.
Thank you.
And since we have our technical problems with Professor Kaygısız is solved, I think, can you share your screen with us, Professor Kaygısız?
Yes, okay.
He will be with us with 2 presentations, I think. The first one is called the performance of solar-assisted dual source heat pump.
Okay, thank you very much. Performance of a solar-assisted dual source heat pump.
We cannot see your screen at the moment. If you want, you don't need to share it, but if you want
to share. Can you see my screen?
No, not at the moment.
At the moment. Why?
There is a share screen in the panel, I think.
Dear Professor Kamil Hoca, you hear us?
Yes.
Now, when you look at the bottom of your screen, you see that there is share screen button.
Green button.
At the bottom,
yes.
Just click on it and share any of your screen, and we will control your presentation.
Is it okay?
Not yet.
Not yet.
Now
is it okay?
Only. Yes.
Only.
You will present from Word Office or another?
Word.
All right, then now you can control it.
Is it okay at now?
Yes, we see.
Yes, we see it.
The performance of a solar-assisted dual source heat pump. Heat pumps all time using as a heating or cooling of buildings or refrigeration. A simple example is a refrigeration in our homes. Heat pumps produce 2 or more heat than the electrical heating. There is some heat sources for heat pump. One is shown here, solar-assisted parallel heat pump. Parallel means that there is two heat sources. One is air and the other is solar. If sunshine is very clear, the solar collector collects solar heat and then go energy storage. After that, go heat pump, and or when out air temperature is high, but day is cloudy, no collector operate, but air source heat pump operate. This is a parallel mode. This is a parallel mode. Parallel mode means that there is two sources for heat pump. One source outdoor air, the other source is solar collector. If the outdoor air more heater than the water obtained from solar collectors, the heat pump use outdoor air as a heat source. When sunshine is very clear and obtained water temperature high from solar collectors, the heat pump use solar collector or solar aided situation as a heat research. This is a storage tank. Storage tank contain water or contain latent heat materials. The other figure, figure 1E and figure 1B, same, but design some different. This is a laboratory, maybe, house, maybe, or a resident, maybe. Sometimes obtained heat or air temperature not enough to heat the room, and then the auxiliary heater is used. The circle is heat pump. As shown, figure 1E and 1B, we show that heat pump all-time use two heat source. One is solar source, the other is outdoor air. Figure 2E shows schematic direct series solar assisted heat pump. Series means that the day is very clear, sunshine is very good. So solar collectors operated from at 6 to afternoon. Obtained heat is high and go to the storage tank and then storage and extra heat go heat pump, or sometimes direct obtained hot water from collectors sent to the heat pump condenser. This is a direct series solar assisted heat pump. Solar assisted heat pump. Storage tank maybe contain water or maybe contain latent heat materials such as saltitrates or fatty acids or paraffins The other design figure to be also the same. Series means that solar collector use it when sunshine is very clear. There is a heat exchanger in room, auxiliary heater, heat exchanger collector from collector cycle, and condenser of the heat pump. This is design is called series heat pump system. The other schematic overview, indirect series solar assisted heat pump. Here, heat pump, solar collector, storage tank. The other section is room or laboratory or any space heating area, Third, dual source. Dual source means that heat pump used to surge. One is air, outdoor air. The other is solar collector or solar photovoltaic, may be possible. At recently, PVT, solar photovoltaic and thermal combination is very useful because the PVT and thermal collectors give us some electricity and some heat. Dual source has advantage. Solar collector advantage or solar advantage and air, outdoor air advantage. In some climatic regions such as Trabzon in Turkey is Iliman iklim. So Iliman means that the outside temperature about 2, 3, 4, 5, 6 at winter days. There is some little 2 or 3 or 5 days minus 0 at winter season. This shows configuration of the latent heat storage tank. There is a lot of configuration. We tested and experimented this configuration. This little cylindrical contains fast change material, calcium chlorohexahydrate. We use it sometimes we use it paraffin wax, sometimes we use it fatty acids, which fast change material is not expensive, very useful, so we can use it. Figure 4b shows variation of stored energy with time at different values of Q in and F in seems fluid. For calcium chloride hexahydrate In this graphic, we can show 3 mass for calcium chloride hexahydrate. 1,000 kilogram per hour, the other 600, and the other 600 kilogram per hour. So if mass is increasing, the stored energy increasing as a megajoule, The other figure 4C, variation of wool PSM melting time with total PCM volume at different values of Q in. PC is radius of the tubes. Radius of the tubes. Depending the radius of the tubes contain phase change material. There is 4 different mass flow rates. There is 4 different mass flow rates. So according to the mass flow rate values, the wool PSM melting time is varying dependent total PCM volume. In figure 5, fraction of the annual load met by free energy. Free energy means that energy obtained from outdoor air or obtained from solar collector by heat pump is a heat research. If day is very clear, sunny very good, we use solar collectors as a thermal collector or PVT collector of each other combination, PVT thermal collectors, depend on solar collector area. The upper line, conventional solar. Conventional solar shows that if collector area increasing, the free energy percent increasing. This is conventional heat pump as constant value, not depend on solar collector, because conventional heat pump all time use outdoor air as a heat source, This is series heat pump, solar assisted heat pump system. This is parallel. Upper line is shown dual source. As shown from figure 5, the dual source has more advantage than the parallel system, than the series system, than the conventional solar system, depending on solar collector area. If solar collector area is increasing, the free energy percent is increasing. But this situation gives us more and more first yatırım cost, initial cost. More collector area means that more investment cost, more energy storage give us more investment cost, and dual source has two sources. It means that there is two investment cost. One is solar collectors, the other is only heat pump. We can use again systems. There is one solar collector or PV, solar photovoltaics is initial cost, need, storage tank need initial cost. Storage tank contains phase change material or ice as a latent heat, ice. This is an initial cost. Heat pump is an initial cost. The other, all of them, initial cost. So when we decided which system beautiful or which system suitable for our aim, we can use economical analysis. We can use economical analysis. For example, life cycle cost analysis, which system more appropriate for me, which system. There is three systems: solar assisted heat pump, series heat pump, dual source heat pump. Which system? There is a lot of criteria for selection. These systems, one of the systems, which system is very useful for me. So we can use some criteria. One is thermal criteria. Thermal criteria shows that dual source has more free energy, dual source. But not these criteria enough, so we can use another criteria such as economical criteria, life cycle cost analysis.
Wait, can we go to the next presentation?
Next, yeah. Okay, maybe.
It's really interesting. There are lots of...
maybe. The other presentation is capric and myristic acid mixture with gypsum bulbar for latent heat energy storage. The Professor Ahmet Sarı is my doctoral student. The other ekip, Ali Karaipekli, the others. This submission will submit by Ahmet Sarı, but there is some problem. So latent heat energy storage recently have more and more advantage, especially energy density at presently low cost. So fatty acids very famous recently. Capric and myristic acid mixture use for more lower melting point.
Are we supposed to see another document? We are still seeing the dual source heat pump at the moment. At the screen, there is a Word document for dual source heat pump.
Figure one shows that two heat comparison. One is sensible heat, the other is latent heat. Sensible heat means that about the same temperature, at the same temperature during the melting, change the phase change means that these chemical materials change its phases and storage more heat, more thermal heat.
Yes, but we cannot see the figure.
This experimental study. Melting temperature and latent heat of capric acid. Pure capric acids have some melting temperatures. A lot of 1, 2, 3, 4, 5, 6. Yes.
We cannot see the figures you are talking about. Şu anda ekranda önceki sunum kaldı.
Yeah.
Önceki Word dokümanını görüyoruz o.
Onu çıkarayım o zaman. Dur, onu çıkarayım. Çıktı mı?
Şimdi tamamen ekranınızı yeniden paylaşabilir misiniz? Altta
tamam.
Share screen.
Okay.
Şu anda ekranınızı hiç göremiyoruz. Sadece yüzünüzü görüyoruz.
Ekran, dur şey inelim bir dakika. Nerede bu? Ha, share screen. Okay?
Yes.
Is it okay?
Okay. Yes.
Okay.
Thank you.
The second summation is capric and myristic acid mixture with gypsum wallboard for latent heat energy storage. If pure capric or pure myristic acids used at the latent heat materials, the melting point high. But we use a mixture with gypsum, in other material, so that the melting point decreasing. The melting point decreasing, as shown figure. Evet, as shown figure 9. This is a decreasing melting point mixture phase change material. Capric, myristic mixture. So this is pure melting point. This is the other pure material melting point, but we mix them some percents. The melting point is decreasing. The low melting point all time is advantage, especially solar assisted heat pump application. For example, we used in some experiments, calcium chloride hexahydrate have 28 or 29 degrees centigrade melting point. In this figure, we show that the capric and myristic acid mixture has very low 21 degrees centigrade melting point. This melting point is very suitable for heat pump assisted space heating and water heating applications, because when we choose low working temperature is good all time. Figure 10 or figure 12 shows us differences in calorimetry cures, fast change, some pure and mixtures, wallboard, a mixture, differential scanning calorimetry, cures. Evet, the melting the temperature varies with time. There is some points, the melting situation. Evet. The red line shows this center of test room with PCM. The black in their center of test room without PCM. It shows that PCM storage as more heat. This is show with PSM experiment. So the temperature change with from 12 to maximum 25. So in theoretical, the melting time or latent heat time temperature is constant as shown in figure 1, as shown in figure 1. Constant latent heat means that the fast change material stored energy as a constant temperature. This is a situation show us theoretical observation, but in practice is not show. In practice show this figure. In practice, this is a practical situation. The figure 1 shows theoretical situation. Table which shows us changes in thermal properties of wallboard with respect to thermal cyclone numbers. Thermal cyclone means that melting solidification. As change material, if salt tetrate, if paraffin wax, if maybe fatty acid, should be give us a flexibility. Melting or solidification will be continue a lot of cycle. Zero cycle, melting temperature 21 degrees centigrade, the enthalpy joule per gram 36-23, but 500 cycle, the melting temperature some decreasing, and enthalpy, value of enthalpy, energy density about same. When after 1000 thermal cycle, maybe constant. These experimental results show that the fatty acid mixtures with wallboard show very good thermal cycling products. So we can say that fatty acids or mixture of fatty acids wallboard is maybe a very good energy storage material in application of solar energy or solar assisted heat pump application as shown figure 1. These figures show us a general observation of the solar-assisted heat pump situation for cooling, heating, or cooling, or heating and ventilating and air conditioning applications. The test unit contains saltitras, maybe contain paraffin wax, maybe contain fatty acids. The selection of the PSM depends on economical criteria and another chemical criteria.
Thank you, Professor Kaygısız.
Okay, is it okay?
If it's okay with you. Our time is limited, therefore I think we can ask you the questions after the session, if you will be if you are available. Thank you.
Thank you. Thank you very much.
Yes, they were very interesting. Especially for me. And the gypsum wallboards are everywhere. So using PCMs to enhance
studies
their performance.
Very interesting. Heat pumps, solar-assisted heat pumps, latent heat thermal energy storage application is very intelligent. All-time energy is very intelligent and very, very loving study area. Yes. Energy means that all-time energy. Yes, okay?
Okay.
Thank you very much. Thank you very much.
Thank you.
Mr. Ayça, thank you.
The next presentation is on microencapsulation of three-component thermochromic systems by Cemil Alkan.
Oh, Cemil. Hello, Cemil.
How are you? How are you, Mr. Kaygısız?
I'm very well. I'm very well.
Okay.
But no, I have any assistant. I am all-time singular man.
Yeah, problems are the same everywhere.
Yes.
As it is here. Okay, thank you for introducing, and my speech will be about microencapsulation of thermochromic systems. And yeah, this is a TÜBA project, and we have been working on another issue of thermal energy storage materials. Microencapsulated PCMs have widely been used in thermal energy storage applications. Here, we think to use them in thermosensor in a thermosensor application, as I said before, it's a TÜBA project. We are together with a textile engineering group here. We are a chemistry group producing and investigating in different aspects of phase change materials. And because that is to apply textile fabrics, this is an engineering study, and we are helping them in producing the microencapsulated species. And the aim of this study is first to prepare some kind of thermochromic systems. They are formed by a solvent, colorant, and color developer. In our study, we think to prepare more environmental friendly systems, and so we changed the color developer from bisphenol A to phenolphthalein in this study. In the material basis, in thermochromic material basis, the originality comes from pH sensitive phenolphthalein material. And here there are some examples of thermochromic materials and their textile applications. Yeah, here there is a colorant. a normal colorant, and when we apply thermochromic materials in microencapsulated form by temperature treatment, it changes its color. And sometimes the temperature may come from human body. In the trousers, you can see that there's hand shape on it. It comes from the heat of a body. And of course, the change in temperature should be reversible. And yeah, in literature, these materials are generally liquid crystals, and some dye systems, gold or silver nanoparticles, quantum dots, or dye polymer blends. We think to study on the most widely used material. We prefer liquid dyes because we have good experience in preparation of phase change material, microencapsulated phase change materials. And yeah, these materials show chromic behavior due to changes in the physical environment that occurs when the temperature decreases or increases. The change should be reproducible. Therefore, the matrix of the system should be stable upon temperature fluctuations. Like liquid dyes, like cyprolactones, cypropyrans, and fluorans, I will not go on details of the structures. They are pH sensitive at the same time, and they are good electron donors, and so they need a color developer. When the system is enhanced, it should give the proton to a counter molecule. And this counter molecule is generally, most preferably, bisphenol A in literature up to this study. And ternary systems based on reversible color change of a color former by means of color developer. Both should be in the system. And as a third, a solvent. Solvent is a phase change material. It changes its physical stature from solid to liquid. And by means of solvent usage, we can adjust the thermochromic phase change temperature or thermochromic respect temperature of the system. Yeah, this is also another advantage that you can adjust the thermochromic phase change temperature in such systems. Yeah, here there is an example of thermochromic material. In the left, it is in colorless state, and when excited, here proton exchange is shown in the system. It may turn its color to colored, but to do this, it should need a color developer in the same medium. Dye should interact to a color developer. At the end of our literature survey, we have found phenolphthalein is more environmentally friendly and proton exchanging molecule, and change it as a counter molecule. Actually, in the project, we have tried many others, but found phenolphthalein is as the most effective one. Here we use 3 different kinds of colorant molecules. We get them from commercial sources and used phenolphthalein. As I said, we use some other color developer materials, but found phenolphthalein as the most effective one, and use 1 tetradecanol as solvent. Because tetradecanol has a phase change temperature at around body temperature. It's around 37, and we think to use such materials as thermal sensors to increase of body temperature. They may be used in some fabrics for children, and they may show illness when they are used in such fabrics. To apply to fabrics, thermochromic systems should be microencapsulated. When you microencapsulate them, you don't need to deal with liquid state of the material. We put the material into polymeric shells. The shell of our system was polymethyl methacrylate. Polymethyl methacrylate is known as plexiglass and colorless. We cross-link it using a comonomer, ethylene glycol dimethacrylate. It's around 4% of the system, 4% of the receipt, so it doesn't affect the appearance of the microparticles too much. And to prepare microencapsulated species, you need a surface active agent. We used polyethylene glycol 1000. Our preferences depend on the cost and availability of the materials also, because this is a project for automotive industry, and so we should use reasonable materials, we need reasonable recipes to prepare microencapsulated species. And we used a water-soluble initiator to initiate polymerization in order to form polymer shell. This picture summarizes the preparation of thermochromic system and microencapsulated Cpsc. As you can see here, first thermochromic system is prepared homogeneously and it's emulsified in polyethylene glycol 1000. And by adding the reactants for shell and an initiator, we can start polymerization. It takes about 4 to 5 hours, and at the end of the polymerization, we go on string for 3 more hours during cooling of the system, and then we get microencapsulated Cpsc suspension. Yeah, we named them according to the materials. Here from the project, we put some names. The last digit in the names shows the type of the colorant, and 1, 2, and 3 according to the colorant numbers. The first 2 digits is are coming from the project. We, as I said before, we tried many of the other systems to prepare thermochromic microencapsulated species. Because we will get fabrics at the end, we should do thermal history test, and so we need a digital camera, and we determine the morphology of the microparticles by using scanning electron microscopy. The mean particle size, diameter, and size distributions were determined by particle size analyzer. And for chemical structure, we used Fourier transform infrared spectroscopy. It's not possible to nuclear magnetic resonance spectroscopy here because the shells are not soluble in any solvent. And thermal properties, thermophysical properties were determined using TSC, as thermal endurance limits were determined by using a thermobarometric analyzer. And here there are the thermochromic systems. We should handle in couples the first 2, black to colorless, red to colorless, brown to colorless. When we encapsulate these species, at the bottom, we can see light black to white, pink to white, and brown to white. As you can see here, we successfully prepared thermochromic systems and encapsulate them to apply different kinds of fabrics. Here, there are electron microscopy pictures of microencapsulated thermochromic systems. The third one seems the best, but as you can see here, there is no leakage of paraffin out of the system. They are all homogeneous. And as you can see here, the particles are unimodular distributed. They are all between 200 nanometers to 50 micrometers. And the particle size analyzer instrument gives us the mean particle size distributions. As you can see here, 90% of the particles are less than 50 microns. Fourier transform analysis were done to prove the synthesis. Actually, it is to show the improvement of the synthesis in paper. When we see the solid materials as here, this is also a proof of the microencapsulation, because if you don't microencapsulate the species, they are all in liquid phase, and you can get this appearance actually. And after infrared analysis, we are in the infrared analysis, we are looking for some specific peaks, if they are there or not, to prove the chemical structure of the microencapsulated species. The most important part of the study is DSC analysis. In the left, you can see the DSC data of thermochromic systems. They are slightly lower than 37 degrees Celsius. And the phase change enthalpy values during melting and crystallization are almost same, because they are homogeneous system. When we encapsulate them, as in this second table, the enthalpies slightly decreases, and also phase change temperatures also decreases. This decrease is due to the cryoscopic effect of the system. If there is anything soluble in the system, as in the left or in the right, the phase change temperatures of the system decreases. And at last, when we look at the thermal Andrews limits of the microencapsulated species, we saw that the materials are very stable up to very high temperatures. The first degradation temperatures are about 260, which are very higher than possible ambient application temperatures. As a result, we concluded, we get some conclusions. First of all, we prepared PMMA microparticles with thermochromic system, and as a second, they are reversible, and they are dark in thermochromic systems, and their darkness turns to light tones when encapsulated. And when we use them in fabrics, they are still showing their thermochromic properties. Also, we have seen that the thermochromic systems, microparticles, had very successful enthalpy values, and these particles can be used also in thermal applications, thermal comfort applications. And phenolphthalein can be used as a color developer, and it was possible to prepare different types of materials. Actually, we applied to some other colorant materials. These are only LECO-based colorants. It worked perfectly in also other different systems. Phase change temperatures of the produced systems were slightly lower than 1 tetradecane, and this is assigned to cryoscopic effect. and coloroscopic effect of any residue from the synthesis and color developer. And at the end, we found thermochromic textiles as thermal comfort materials to be used, to be exploited in different kinds of systems. For this study, we are thankful to TÜBİTAK. They support TÜBİTAK, which supported our project. And also thank you all of you for your patience. I can answer if you have any question.
Thank you, Professor Alkan. I see that Önder Yargı has a question.
Yeah, thank you. Thank you for the interesting speech. I will have just one question. Is this thermochromism process new technology or currently be applied to similar systems? Because we hear some similar systems about cosmetics or toy cars when we heat, when we expose to the hot water.
There are some thermochromic fabrics also in the market, not in the literature, even in the market. But these are new materials to be applied to all, to any places. And the most interesting point is that you can adjust the phase change response temperature here by using phase change materials. Also, they are hybrid materials. It is possible to thermoregulate the system by using these fabrics.
I understand. You can arrange the situation.
Yes.
Thank you.
Thank you, Professor Alkan.
Thank you.
I also have a small question. I think I have to look at the time, but we see that thermal conductivity is a limiting factor in the use of PCMs in many other applications. Is this also true for this project?
Yeah, we are using some N-alkanes in microencapsulated Cpscs. They are isothermally working species. When we microencapsulate them, their thermal conductivity, of course, decreases, but the particles are so small that thermal conductivity do not affect its isothermal working conditions. It responds at the shortest time due to extended surface area and small particle size. Some PCM salt hydrates or some organics like polyethylene glycose show overcooling, but paraffins do not show overcooling. And when you encapsulate, you don't need to add any thermal conductivity additives because they are isothermally works, absorbs heat and release at the same temperature, almost at the same temperature.
Thank you.
Right.
Our next speaker is Naziran Güre, or Nazenin. I'm not sure about the pronunciation, sorry. The climate impact of blockchain in the view of cryptocurrencies is our topic.
Hello, let me share my screen to begin with. Yesterday, Aziza Akyol asked me to introduce myself, so I'm better prepared for today. I'm a research assistant in mechanical engineering in Beykent University and CEO of Enhance Limited. My Bachelor of Science is in Environmental Engineering, both Bachelor and Master is in Mechanical Engineering, and I'm a PhD candidate in Electrical and Electronics Engineering. And my Master of Thesis was published in USA's leading piezoelectric company. My scholarship is supported by TÜBİTAK. My startup is supported by Ministry of Science, Industry and Technology. And our ended project is awarded in international Team Award in Climate Launchpad in Edinburgh, United Kingdom. I have 5 national awards and 3 of them belongs to different blockchain projects. I have also participated MIT Bit Pandemic, EU versus Virus, Pan-European Hackathon, Florida Sunshine Hackathon, and Facebook F8 Refresh Hackathon. I'm the lead inventor of 2 awaiting patent applications, and my latest research is published in Silicon Valley. Today, I will be presenting you climate impact of blockchain in the womb of cryptocurrencies. Just a second. Blockchain evolution is actually started in 1979 with Merkle 3 patent. Then it is improved into cryptographic chain by Haber and Stornetta in 1991. An important name is Zabonic, also known as Nick Szabo. 10 years ago, the Bitcoin paper invented Bitcoin coin on partly decentralized pre-Bitcoin structure. And then our Turkish professor Emin Gürtsirer, 5 years ago, Bitcoin invention in Cornell University, also find Karma, a peer-to-peer distributed hash table, digital currency, with proof of work mechanism, which is the current mechanism of Bitcoin. On 31st of October 2008, Bitcoin first released. As you can see here, Satoshi Nakamoto is the nickname and no one knows who is the inventor of the Bitcoin actually. And here you can see it uses CPU power. Nowadays, it can both use CPU or GPU power, and to have better performance and for energy efficiency, application-specific integrated circuit chips, also known as ASICs, are used. The real reason for Bitcoin to consume energy is that it is based on proof of work consensus mechanism, because this depends on CPU or GPU power. And the devices has to solve the hash puzzle and find the blocks. Meanwhile, they consume energy and generate an enormous amount of wastage. And miners profit upon block rewards when they find the blocks, also upon transaction fees. When we see, actually to begin with, since CPU power is needed and since it is solving hash puzzles, this hash is coded in a dynamic way. As the more miners get into the system and the more better performing ASICs get into the system, hash rate and the difficulty increases. Here we see the mining difficulty is directly proportional with the hash rate, and it is also proportional with the electronic waste because those devices are heating up and have tendency to be broken. Also, they have to revise their ASICs to consume less energy and for better performance, otherwise they couldn't make profit upon it. This is also same with Ethereum network as well. It has also dynamic hash rates. And when we come to ASIC evolution and related electronic waste, before the Bitcoin highly popular in the beginning of mining, even the USB antminers were available, USB mining were available just as PCs and etc. And then USB antminers upgraded into sets. Meanwhile, laptop mining regained attention lately due to chip crisis. And after 2017, Bitcoin prices inflated. Many investors get into the mining farm businesses, and they have gigantic mining farms to profit upon. Nowadays, improved heat exchanger versions of giga hash rate USB sticks are also available for mining. And prior to getting to blockchains, climate impact, let's begin with the climate impact of currently used digitalization. Single Google research emits 0.5 gram of carbon dioxide, and each second 63 kilo Google search is performed, and which equates to 2 trillion a year. And we need to multiply 2 trillion with 0.5 gram, that is just Google search, result in 1 trillion gram of carbon dioxide. And when 100 pieces on 24-hour run, emitting more carbon dioxide than European car exhaust emission limit. When we come to data centers, it is estimated that the total power consumption of data centers is equivalent of 3% of global energy consumption, 9% of energy consumption of France, and 260 megaton annual carbon dioxide emission. To begin with, Bitcoin mining consume 0.15% of global energy consumption. Please pay attention that this is 20 times lower than data centers. Maximum Bitcoin electricity consumption is estimated as around 90 terawatt-hour per year. However, re-estimations may drop it to around 70 terawatt per hours. And how much is this when we try to imagine it? It is equivalent of the energy consumption of Denmark or Belgium or Chile, even exceeding Hungary and all the other nations, countries you see here. Energy consumption of mining and transaction of Ethereum is actually lower than Bitcoin, much lower than Bitcoin. And we need to pay attention that since market cap is occupied by 8% of Bitcoin and 10% of Ethereum, since when they combine, they would reflect 90% of the action, evaluating those two would give enough perception. So it's equivalent of Georgia, country of Georgia's electricity consumption, and single Ethereum transaction is equivalent of single daily electricity consumption of United States house size. And Bitcoin carbon footprint is 7 times less than data centers carbon footprint, but still it is not so small to be ignored. Actually, it is very much. There is 40 megaton carbon dioxide per year, and it is equivalent of New Zealand's carbon footprint. In terms of electronic waste, it is equivalent of Luxembourg, which is annually 10 kiloton. Single Bitcoin transaction electronic waste results in 30 grams, and carbon dioxide emission is about 300 kilogram. Just one money transaction, this means just one Bitcoin money transaction power consumption is around 700 kilowatt per hour, which is equivalent of 24 US size house per day. You see the waste heat here, and miner actually opens its door even in winter, even in snowy weather, and the snow melts on the roof. Previously, it was proposed that around 8% of Bitcoin mining is empowered by renewables or cryptocurrency mining, but this is corrected as 40%, like decrease as half, and the rest is sourced from fossil fuels. When we see the distribution of renewables, we see that hydropower dominates, and it is followed by wind, solar, and lastly geothermal. For fossil fuel mining, coal and natural gas dominates, and the rest fossil fuel sources. When we check electricity prices, though Bitcoin is aimed to be decentralized, that's why decentralized finance is popular. Actually, in practice, they can be locally centralized due to cheap energy is seek to be profit upon. So the localization is mostly in China, and then followed in USA, and then Russia, and like Kazakhstan, Iran, and other Ukrainian sort of coal countries. And there is another estimation debate of single money transaction of Bitcoin to single money transaction of Visa. When they ratio this, first of all, in New York Times proposed that Bitcoin is like 1 million times more consuming more energy than Visa. And then reevaluations result in 4,000 and even deeper estimation result in 2,000. The reason is that first estimations didn't account that the employees of Visa and the PC's electricity consumption of those employees and buildings electricity cost of those structures as well. So when we say Visa and we say human source systems, we have electricity consumption by many means. But in blockchain, it doesn't have this, and all the transaction and actions are totally transparent. So exact amount of power consumption of Bitcoin is can be calculated. Still, when we take the minimum amount, it has to be mentioned that it is 2,000 times of Visa, which is not, which is still not low to be ignored. So what can be the possible solutions? Yesterday, I proposed my other subject, that is considering state of art in green cryptocurrency mining. They can use the waste heat to greenhouse crops, or some in the right-hand side, hydropower plants adopt Bitcoin and triple their profit. And like heating systems, that you do not have to pay the heating system because cryptocurrency profit already covers the electricity costs. And my suggestions is use of Peltier as a cooler for ASICs and mining rigs, as well as thermal energy generation from Peltiers from waste heat of ASICs. And this is the possible configurations of thermal electric generation together with the fan cooling for ASICs. Its adaptation is also applicable to Canadian van ventilation, which is also integrated with greenhouse for mining purpose only. And this can still possible for energy generation upon heat difference. So ultimate case can be fully sustainable, which is also issued yesterday. And another important point about possible solutions actually lies in the nature of the Bitcoin, because Satoshi already limited it with Bitcoin supply at 21 million Bitcoin. And we are already in around here, and we mined by the end of February, we will be mining almost like 19 million Bitcoin, which means which means almost equivalent of maximum saturation. There is 95%. So even though Bitcoin mining would carry on after 21 or 22, it wouldn't be even more than 2025. So the maximum duration of Bitcoin mining, unless it hyperinflates in the value, would be no longer than 2025. And this is also reported by FBI. Those figures are from FBI report. On the right-hand side, you see that just for two Bitcoin, there is the saturation like 20.999 million to 21 million. You need 40 years, so no one would be mining in these durations. There is another solution in Ethereum. This happened last year. This is initiated by the founder of Ethereum, Vitalik's environmental concerns about climate, and they changed the consensus mechanism. Just by changing the consensus mechanism, they reduced the computational power needs, and instead of depending it from the stakeholders' stakes, that is how much Ethereum a stakeholder is holding, and they can decide the decentralization nature. As a result, they eliminated GPU, CPU power need. Only servers and storage devices would consume energy. Thanks for your dear attention. That's the end of my presentation. You can connect me with any of those emails.
Thank you. That was a very interesting topic. not very commonly seen. Your ideas are need much thought processing for me to understand. Maybe I will listen to your presentation once more.
I would love to repeat if you want me in the end.
If there are no questions, I would like to give the microphone to Professor Adnan Midilli for the topic on a policy on renewable hydrogen ecosystem in Turkey.
Thank you. So first of all, I have to share my screen with you. You see it very well?
Yes.
Okay, then. I am sharing in. Everything fine to see?
We are also seeing the, yes, okay.
Okay.
Next slide, but it's not.
But this one is problem for me.
We were seeing it, but at the moment only the central slide is seen.
Okay. Okay, ladies and gentlemen and dear listeners, actually welcome to my presentation. And meanwhile, I would like to thank the chairman. Thank you. First, I will actually present a presentation entitled Policy on Hydrogen, Renewable Hydrogen Ecosystem in Turkey. It is a very different subject for us. First of all, as an outline, I will talk about the objective and basic concepts, and then I will actually discuss why Turkey needs a renewable hydrogen ecosystem, and then we will discuss what are the challenges for a renewable hydrogen energy ecosystem, as you see here. And then we will talk about the basic conceptual design of a renewable hydrogen energy ecosystem, considering the components, dimensions, structure, functions, and stakeholders. And then I will talk about some strategies and policies for renewable hydrogen ecosystem roadmap. And then I will finish actually my presentation with results and discussion and concluding remarks. What is the main objective of this study? Actually, we try to develop some policies for establishing a renewable and a hydrogen energy ecosystem in Turkey. So before actually we develop this one, we have to pay more attention for better understanding the main concepts and the basic concepts. And if we have hydrogen energy ecosystem at that time, we have to understand some important concepts including management and energy sources, what kind of energy sources we have, and the supply chains, what kind of supply chains for hydrogen energy ecosystem, and later I will talk about this one. And services, what services are important for this type of the ecosystem, and the markets are very important. And also we have another important concepts, active key drivers and the passive key drivers, and I will talk about both of them. First of all, let's look at the hydrogen studies level in Turkey, and you can see when you actually investigate the Google or literature, you can see some scientists, some researchers, some PhD students working on hydrogen individually. So actually, we have level 1 in Turkey. When we look at the level 2, here we need some groups. And you can see some working groups on hydrogen at the universities, in the research and research centers and the institutions. And also we have this one. And when we look at the level 2, 3, so actually we have a hydrogen community in Turkey and working on different subjects, different aspects of hydrogen energy and technologies. And also we established National Hydrogen Association in Turkey in this regard. And now what we need to extend this community to ecosystem. And in order to create a renewable hydrogen ecosystem, what we need, what kind of strategies we need, actually, what kind of challenges we have to overcome, I will talk about later in detail. First of all, I would like to actually describe what is the renewable hydrogen energy ecosystem. Renewable hydrogen energy ecosystem is a stable, renewable, sustainable, techno-ecological system. This system creates some interactions. Interactions is very important between all components and stakeholders. And these components and these stakeholders should be related to the renewable energy supported hydrogen energy, and also between the livings and non-livings. A few minutes ago, I mentioned about the passive key drivers and the active key drivers. They are actually in the living environment and non-living environment. So, the interaction should be clean and balanced, efficient and economical and sustainable. At that time, we can mention about the renewable hydrogen ecosystem is a really important concept for hydrogen among the hydrogen studies. Okay. Let's look at this one. Why Turkey needs hydrogen energy ecosystem? First of all, let's look at the reason one. What we see here, we see actually important description, including energy dependency. And Turkey should reduce the energy dependency, and Turkey is paying more attention for reducing the energy dependency by applying renewable energy, including solar, geothermal, wind, and hydropower, etc., and the biomass. And the first reason is we need actually to reduce the energy dependency. And also we need to develop the domestical and local national energy technologies. And this is important for Turkey. And also, if we do this, at that time, maybe we can become a global energy gamer all over the world. And when we look at the reason two, what we see here, we see actually the COVID pandemic. During the COVID pandemic, when we look at the literature, we can understand that some countries try to change their fuels into actually carbon-free fuels. At that time, therefore, Turkey should do this one. This is another important reason. When we look at the reason three, what we see here, we see energy sustainability. Energy sustainability is very, very important for all countries. So Turkey tried to actually ensure energy sustainability in Turkey by extending the energy resources and energy use, renewable energy use in Turkey. And also what we need actually the cleaner fuel, cleaner energy, cleaner food, cleaner environment, and the cleaner air, cleaner water for a sustainable future. Therefore, Turkey tries to do this one, and this is another important reason. And when we look at the reason four, what we see here, global warming. and climate change. Nowadays, we listen the news and the mention about the global warming all over the world. This is really important. And also the countries try to change their energy use into carbon-free energy sources and carbon-free fuels. Therefore, the global warming global warming effects should be reduced, and our country tries to do this one. And this is another reason. And when we look at the reason 5, what we see here, we see the renewable energy ecosystem, and then a renewable energy ecosystem. When we look at the Turkish side, Turkey has a solar. Actually, we produce solar cells, solar power plants, wind power plants, geothermal power plants in Turkey. We developed all these power plants in Turkey. So it means Turkey has the renewable energy ecosystem already. Therefore, we need to increase its performance. How can we do it? By using this renewable energy ecosystem, and we can actually add the hydrogen ecosystem. At that time, we can establish a renewable hydrogen energy ecosystem. While we are doing this one, we will try to increase the performance of the renewable energy ecosystem. This is important reason. And reason 6 actually is directly related to the green hydrogen production. And what we know that actually Europe has paid more money for actually production of green hydrogen. And in the future, I believe that Turkey will export green hydrogen to Europe. This is important aim for us. Actually, we can extend all the reasons. Just here, I mentioned only 6 one. Okay, let's look at this one. This is important. What kind of challenges we will have if we actually before we establish the renewable hydrogen energy system? What kind of energy problems in all over the world? You see, we have some important problems: decreasing energy security, as you see here, and energy cost, and energy pollution, energy shortages, environmental pollution, global warming effects, waste of the sources. These are really important problems, really important energy problems in the world. And these are causes the depletion of the economically available energy sources. At that time, we have to find a better solution to get rid of all these harmful effects, to overcome all these problems. As you see here, I actually try to show all the problems in 7S plus D. What is 7S? 7S includes source problems, sectoral supply problems, energy sharing problems, energy security problems, energy service problems, sustainability problems, and demand problems. And all these problems causes the energy instability. Energy instability causes the negative effects on the social, environment, culture, everything what we have. Then we will have some important problems. Therefore, we need to establish this kind of ecosystem in Turkey after that. Now, I will talk about the basic conceptual of renewable hydrogen energy, basic conceptual design of renewable hydrogen energy system, and what kind of sectors we have for the hydrogen energy ecosystem. Management and security is important. Energy source sectors, solar energy, wind energy, and others. And also supply chain sectors, energy supply chain, feed supply chain, technology supply chain, and are very important sectors. And service sectors are important, market sectors are important, and active key drivers are important, and passive key drivers are very, very important. And now I will talk about the key dimensions of renewable hydrogen energy ecosystem. What kind of dimensions actually a hydrogen ecosystem will have, starting from the science and technology to employment and the qualified person. As you see here, we have many, many dimensions, including health, law, security, ethics, education, as you see here, environment, flora, livings, and source and market. These are important dimensions. While we are established such an ecosystem, hydrogen ecosystem in Turkey or everywhere, so we have to pay more attention for better understanding this important dimension. Okay, now actually I will talk about the infrastructure of the renewable hydrogen energy ecosystem. First of all, let's start with this one. What we have here, we have management and security infrastructure. So we have to establish the management and the security infrastructure. Why? Because we need to operate the system very efficiently, and we need to develop the smarter systems, and we need to actually reduce the harmful effects of the technologies, and also we need to use the artificial intelligence and machine learning and big data, and all others should be included here, and therefore management and security infrastructure very, very important. Another important infrastructure is the qualified person research, innovation, and training infrastructure. And why we need this one? We need to actually increase the performance of the ecosystem. And another one is infrastructure of data, information, and knowledge for more scientific production. Production is important. Scientific production is very important, because we need we have to perform the production of hydrogen, and technologies what we need should be mainly based on the knowledge, scientific results. Another one is resource and feedstock supply chain infrastructure, and technology infrastructure is very important for multi-purpose production. Another one, actually, the stakeholders infrastructure is very important. Why? Because we actually need to empower the stakeholders, and we need to generate energy coefficiently by performing the coefficient production. And also we need actually to develop some technologies together. Therefore, we have to establish this kind of infrastructure. Another one is service infrastructure for higher customer satisfaction is very, very important. Customer satisfaction is very important for this ecosystem. And market infrastructure is important. And also another one, communication infrastructure for active key drivers to participate in the process and functioning in the of the ecosystem. And the security infrastructure is really important. And finally, the policy and strategy making infrastructure is really important for nationalization, industrialization, and internationalization and globalization. Now, I will talk about actually some functions of renewable hydrogen energy ecosystem. As you see here, the renewable hydrogen energy ecosystem, the main functions of this ecosystem is leading, planning, controlling, marketing, and services. They should be smart. What does it mean? should be smart. S means sustainable, should be sustainable, should be manageable, should be affordable, should be renewable, should be trainable. And the renewable hydrogen energy ecosystem should actually develop technology, should develop systems, should generate power and heat, and should produce fuel, commodity, and service, etc. They should be realistic and understandable. This is really important. You can produce something, but if it is not realistic and understandable, you cannot actually sell it, and you cannot gain any money. And they should be simple to construct, and they should be easy to operate and apply. All this, I am actually this, should be eco-efficient and environmentally friendly, and they have high efficient systems, and also they should be low cost, and they should be changed into high added value, and also they don't produce any emissions. This is really important, and the customers should have high satisfaction. These are really important functions for renewable hydrogen energy ecosystems. While actually I am saying the active and the passive key components, I mean actually government, municipality, policymakers, media, private sectors, universities, research centers and institutions, financial institutions, etc. And another one is passive key components. Environment is important for this ecosystem, and flora. We have to pay more attention for flora, and animals are important. Livings, air, water sources, and food sources are very important passive key components in the hydrogen energy ecosystem. We have to protect them. This is really important job for us. While I am saying the supply chains, I mean actually renewable energy technologies supply chain, including everything, production, storage, distribution, transfer, consumption, everything. And renewable energy supply chain, as you see here, and the renewable hydrogen technologies supply chain, and renewable hydrogen integrated full supply chain. These are really important supply chains for renewable hydrogen energy ecosystem. While I'm saying the markets, they should be eco markets, and energy producers, energy consumers, steel industry, defense industry, including everything, and exporters and importers. And also eco services, while I'm saying the services, I mean maintenance and operation service companies, innovation and improvement service companies, management and control service companies, the demand and supply service companies. Okay, now I will talk about some key strategies and policies for renewable hydrogen energy ecosystem. I actually separate in 3 phases. In first phase, the most important thing in between this year for Turkey, for example, we need to actually establish the hydrogen technologies in manufacturing infrastructures are important for us. And also, we have to perform the competitive optimization of hydrogen production cost. And in the first phase, we have to perform all these important jobs. In the second phase, what can we do? First of all, we need to actually show the demonstration of the industrial hydrogen system, particularly commercial demonstration of the hydrogen industrial hydrogen system in the ecosystem. And also we can actually between these years, we have to transport hydrogen via natural gas lines. So in Turkey, and there are some laboratory research on the hydrogen injection in natural gas. And our Professor Ibrahim Dinser, and is working on this subject in Konya. And he actually developed a really interesting system for Turkey. This is the first step. It was the first step. In the future, they will actually develop another important steps for Turkey. And in the third phase, between these years, we can establish the steps for hydrogen economy. At that time, we can transit to hydrogen economy between these years, maybe early, I don't know, but this is just a strategy and policy. And also between these years, we can export hydrogen and hydrogen-based synthetic fuels and their technologies. This is another expectation actually for this strategies. Okay, I am showing the renewable hydrogen energy ecosystem steps and infrastructure. Renewable management, renewable energy sources, and the renewable energy technology supply chain, renewable energy source supply chain. This is renewable energy, hydrogen energy sources, as you see here. And these are active key drivers and passive key drivers, and the renewable hydrogen ecosystem covers everything. So our job is really difficult to establish such an ecosystem. And I would like to show, I like this one, and I would like to show the qualitative illustration of transition to renewable hydrogen energy ecosystem. If we transit to renewable hydrogen energy system, this is the actually shows the level starting from 0 to 1. This is qualitative illustration. What we see here, environmental impact of fossil fuels in Turkey, global warming effects caused by, and increasing clean fuel demand. And transient to renewable hydrogen energy ecosystem, when we try to transient to hydrogen energy ecosystem, at that time, these negative impacts will decrease, as you see here. And while we are increased the transition level, at that time, what we see here, we will see ensuring energy independency of Turkey, and the level of energy play major role will increase as well, and energy sustainability level in Turkey will increase. Actually, renewable hydrogen energy ecosystem will contribute to ensure energy independency of Turkey and ensure the energy sustainability in Turkey. This is just a qualitative illustration for better understanding the effect of the renewable hydrogen energy ecosystem. As a conclusion, first, actually, we have some, in order to establish the renewable hydrogen energy ecosystem, the basic conceptual framework should particularly include the smart management of hydrogen ecosystem and the applicable hydrogen policies and the hydrogen ecosystem security and the hydrogen ecosystem sustainability. In this regard, these are important, establishing the resource and data and the information, knowledge, technology, and marketing system related to hydrogen energy, empowering the stakeholders, and establishing a hydrogen market economy based on the internationalization. These are the references. Many thanks.
Thank you for the very detailed.
Very detailed, yeah.
Well, I was thinking about some questions, but then you answered them in the next slides. So I will not ask them. And it's a very intriguing policy proposal. We can, of course, take questions from other participants.
Okay.
But I think everyone wants to go to lunch, and there are no questions at the moment. Thank you, Professor Mideli.
Thank you, Ms. Ayça.
Hope to meet you at the panel.
Hopefully. Thank you.
Thank you.
You're welcome. Bizim sistem bozuk ya. Niye açamıyoruz?
Okay, this is the end of our session.